Hello and welcome back. This is the third and final video discussing quadric surfaces and the last video of this section. In this video we are looking at hyperboloids. So remember, paraboloids, two of the basic traces were parabolas and the third was either an ellipse or a hyperbola. With the ellipsoids, every basic trace was an ellipse. With hyperboloids, two of the traces will be hyperbolas, and the third, well, it turns out the third is either an ellipse or it's empty. So this gives us, well, sort of two or three different kinds of hyperboloids. I'll show you what I mean in a second here. Let me jump down. There's our elliptic paraboloids, the hyperbolic paraboloids, hyperboloids. So there's sort of two main varieties of these hyperboloids, hyperboloids of one sheet and hyperboloids of two sheets. The hyperboloids of one sheet, we're going to see there's a couple different kinds of these. One is just hyperboloid of one sheet. The other is a sort of degenerate form of this, and that's an elliptic cone. So I'll try and show you where all three of these kind of come about. Let's jump to a specific example, hyperboloid of one sheet. These are characterized, so they have this sort of form. We have x squared term, y squared term, z squared term equal to 1, and one of the terms is negative. The other two are positive. So something like this one here. And let's investigate it as we've investigated the other ones. I'm going to start with traces parallel to the xy plane, and I'll start with the xy plane itself at z equals 0. Here we'll end up with x squared over 9 plus y squared over 4 equal to 1, and that gives us an ellipse. So we get an ellipse at the xy plane. If I change my z, so let's say z equal to 1 or negative 1, it won't matter because my z is squared. I'll get the same thing either way. That'll give me a negative 1 here. I'll add that over. That'll give me a 2. And so it'll look like x squared over 9 plus y squared over 4 equal to 2. Remember, we can divide that 2 across and see that this is really an ellipse that's just a little bit wider. So I'm going to say wider ellipse, both in the x and y direction. It'll be wider. And that's at 1 and negative 1. Same thing for 2 and negative 2. It'll be wider yet. And the fact that these come in pairs, positive, negative, we get the same thing. This z squared thing means we have a symmetry about the xy plane. So above the xy plane, below the xy plane should be mirror images of each other. If you think of the xy plane as like, it's like a mirror. So that's these sorts of traces. One's parallel to the xy plane. We get ellipses. In the other two directions, we'll end up with hyperbolas. So what if I set, say, x equal to 0? What'll I get? I'll get y squared over 4 minus z squared equal to 1. That gives me a hyperbola that we can graph. And for these, by the way, in this video, I'm not going to graph all of these. We'll instead just look at figures in the text. But I want to show you where these traces come about. If I set y equal to 0, now I'll get x squared over 9 minus z squared equal to 1. Again, we get a hyperbola. That's sort of the important thing of a hyperboloid of one sheet. It might not be clear yet what's the difference between one sheet and two sheets. Where does that come about? Well, first, I'm going to change my scenes here. There is our hyperboloid of one sheet. So let's take a look at the traces here. So this is the equation we're looking at here, 4, 9, and a 1 on the z squared. Again, these are just constants in general. We can think about how it's going to affect it by looking at the equations and computing traces. So there's our ellipse in the xy plane. As I move my z up, I'm going to get wider ellipses in both x and y directions. If I move down, I get reflected about the xy plane, right? So there we have the same ellipses. Let's look at traces in the xz plane. We get the hyperbolas. We can move these. We'll get hyperbolas as well. If I look in the yz plane, again, I'll end up with hyperbolas. So that's the idea for a hyperboloid of one sheet. So what's a hyperboloid of two sheets? Let me change the scene back. So in general, they look like this. The key thing to look out for here is it has this form. One of the terms is negative. So you can think if I added the negative here to the y, it would instead of sort of being along the z-axis, this would change it to being along the y-axis if this were made negative, or along the x-axis if this were made negative and the other positive. Hyperboloid of two sheets has two of the terms being negative. So I'll work with this example here, and again, we'll play around with it. So I'll set z equal to 0, and I'll get out negative x squared over 4 minus y squared over 9 equal to 1. Think about this for a second. Do you recognize this? There's no solution to this, right? X squared is non-negative, y squared is non-negative, so if I make both of those negative, I'll get a negative over here, or something that's non-positive, right? It could be 0, but it's certainly either negative or 0. That can't possibly equal 1, so this is no solutions. So what that means is that the surface does not intersect the xy plane. Interesting. Let's move up. How about z equal to 1? If z is equal to 1, remember we have the symmetry here in the z. 1 or negative 1 will generate the same thing, so I'll just consider both of them. I get negative x squared over 4 minus y squared over 9 plus 1 equal to 1. So I'm going to take that plus 1 and subtract it the other side. I get this is equal to 0. Well, how could this be equal to 0? The only way is if x and y are both 0. So that gives me 2 points, 0, 0, 1. And 0, 0, negative 1. These are the vertices of a hyperboloid of two sheets. So this one has vertices in it. Hyperboloid of one sheet did not have these, traces that were just a single point. So let's maybe jump up to z equal 2, or let's say negative 2. Again, same thing will happen in either case. We'll end up with negative x squared over 4 minus y squared over 9. Plus z squared, that'll be 4. I'm going to subtract that over, so I'll get a negative 3 on the other side. Equal to negative 3. I want this to be a positive 1, so I'm going to divide everything through by negative 3. That's going to change these to positives. We end up with what? X squared over 12 plus y squared over 27 equal to 1, which we should be able to recognize is an ellipse. Again, we get the symmetry about the xy plane. So we'll have an ellipse of this form at 2 and at negative 2 for z values. As we increase z above 2 or below negative 2, we'll get wider and wider ellipses. Right, because I'll be subtracting those over. This will be bigger and bigger negative values. When I make it negative, it'll be wider and wider. So we're seeing ellipses along the z-axis here. Let's let x equal 0, what will I end up with? I'll end up with negative y squared over 9 plus z squared equal to 1. That's a hyperbola. And if I set y equal to 0, I'll get negative x squared over 4 plus z squared equal to 1. Again, that's a hyperbola. If you're not recognizing that these are hyperbolas, make sure to jump back to chapter 12 or watch those introductory videos for this section. So we get these hyperbolas. And then, so this is the big thing, is we have no trace at the xy plane. We get vertices at 1 and negative 1, and then we start seeing ellipses. So can you imagine that? Try for a second to imagine it, what it's going to look like. And then I will reveal here. Oh, that's still the hyperboloid of one sheet. Right, the idea is if we sort of had a sheet just made out of rubber, we could kind of deform it and make it look like this hyperboloid of one sheet. You can get it from just one sheet. Here is my hyperboloid of two sheets. I need 2 sheets of rubber in order to make this thing. And we can see the fact that on the xy plane, there is no intersection. We need to move z, right? So I'll set z equal to 0, z equal to 5. There's our ellipse. Z higher than 5. We get bigger ellipses. And that's because I'm not looking at the same thing. I'm looking at this equation. So here I've actually shifted my vertex to the right 2. So it's a little bit different. I've shifted it to the right 2. That's why it's sort of over here. And my z value, my constant on the z, my c value is different. And so that's why we need to consider bigger z values to actually get intersections. Right? Between negative 5 and 5, there won't be any intersections. Here's negative 5, ellipse, or negative 6, and a little bit wider of an ellipse. If we look at traces in the other directions, we should see hyperbolas. And we do. I don't know why the trace isn't showing up here. That's weird. but we get hyperbolas there as well. And same in the other direction. These traces, we should also get hyperbolas. Okay, so that's the hyperboloid of two sheets. Again, we can recognize that 2 of the constants are negative. Again, imagine if you swap a couple of these, it's going to change the orientation of it. We can figure out that orientation by just computing some of these traces as I've done here. So last one is the elliptic cone. So it has a form looking like this. Looks a little bit different than the other ones. There'll be an activity this week, hopefully, where you'll sort of see the connection between all 3 of these things, how they all fit together. But for right now, let's just compute some traces. So let's say set z equal to 0. What do I get? X squared over 4 plus y squared over 9 equal to 0. The only way that happens is at 0, so I get a point. Let's set z equal to, say, 1. Then I will get, what, x squared over 4 plus y squared over 9. 1 or negative 1 will generate the same thing, equal to 1. And there's my ellipses. If I bump this z up above 1 or below 1 or below negative 1, I'm going to have x squared over 4 plus y squared over 9 equal to, what will this be, 4 or negative 4? Or sorry, no, it'll always be 4 with this. I can divide that 4 over, and this will be a wider ellipse than above, right? Wider than this ellipse. So we have this widening effect, but now let's look at my other traces. So let's set x equal to 0. I get y squared over 9 equal to z squared. Let's take square roots on both sides and keep in mind it's not a perfect inverse. If I take square roots, I'll get z equal plus or minus y over 9. So that is a pair of intersecting lines. So rather than hyperbolas for these traces, I get intersecting lines. But again, we can think of intersecting lines as degenerate forms of hyperbolas. That is the idea. So here we'll get, what, x squared over 4 equal to z squared. I'll get a similar effect. Z is equal to plus or minus 1/4 x. And again, that's intersecting lines. So instead of hyperbolas, we're getting intersecting lines. Let's take a look at what one of these things looks like. Good, I remembered to switch the scene back. So there's our hyperboloid of 2 sheets. Let's jump to the elliptic cone. So there's an elliptic cone. This is one where the x is over on the other side, right? And the y and the z are on the left side added together. So that means this is going to be along the x-axis, and we get these intersecting lines. So let's take traces. There's my intersecting lines there. I can move my z a little bit. I get intersecting, then I get hyperbolas if I change that. If we look at traces in the other way, I get intersecting lines. And here, if I do my, this is the x1, this corresponds to our z in the example I just looked at, we get our ellipses. So that's the idea with the elliptic cones. It's like a degenerate form of a hyperboloid of 2 sheets, where the hyperbolas are intersecting lines rather than strictly hyperbolas. Okay, that is it for this video and for the section. Thanks for watching. Hopefully this helped. Again, remember the big point here is not to make perfect, faithful drawings of these things, but to be able to go back and forth between the equation and the surface, and then the other way as well, the surface to the equation, be able to recognize those and at least form a mental picture for these things. This is going to be important later on when we start integrating over surfaces and things like this. So we'll get to that stuff later on in a later chapter. Hope to see you there.